Hello, my name is Vivek Bhatia, and this is the presentation for my final term project for the course CSCI E-95 compiler design for spring 2018. So a really quick overview of VCC. It's supposed to be a compiler for a subset of the C programming language. It's developed completely in C++ and requires Flex and Bison for scanning and parsing of the input code. The build files for creating the compiler binary are provided along with the source code. And here is a list of all the command line options which are available as part of the compiler. So the -s flag can be used to specify the stage of the compiler, the default of which is MIPS. The lowercase o can be used to provide a path to the output file to write the output of the compiler. You can also specify the method for the input file, which can be either a file or just to stand it in. And the uppercase O can be used to enable optimizations, the default of which is disabled. This slide discusses the various stages which have been implemented as part of this compiler. Any input given to the compiler is first passed through the scanning stage, which converts the input code into lexemes or tokens, and the output of which is a list of the detected tokens, the type of the tokens, and the converted values. After that, the tokens are then parsed to create an abstract syntax tree. The output of the parsing stage is the input character stream as represented in the abstract syntax tree. The AST is then passed through to the symbol stage, which generates the syntax tree with symbol tables. The end of symbol table output is the full list of the string and the file procedure block scope symbol tables. And also the input stream with references for each variable to the symbol tables. After that, the input is passed through the type checking phase, which basically verifies the type of each symbol and also applies any conversions if necessary. The AST is then passed through the IR stage, which then converts the AST to intermediate representation code. The output of the IR stage is a list of the IR codes. The IR codes are then fed to the MIPS stage, which converts the IR code into assembly code, and the end of which we get a executable assembly program written in MIPS 32 assembly. Next, we talk a little bit about the optimizations which have been implemented as part of the VCC compiler. The optimizations are limited to the IR and MIPS stage only. First, discussing the IR optimizations, the basic stages which have been implemented as part of the compiler are constant folding, algebraic simplification, which includes multiply by zero operations, identity operations, binary operator simplifications, unary operator simplifications. There is also a stage for evaluating conditional expressions, which can be evaluated at compile time. And the final stage is dead code elimination, which eliminates redundant load store operations, unreferenced labels, unreachable code, unused temporaries in the code, redundant jump operations, and redundant labels. The general workflow for IR optimizations is that each stage is applied in succession. And at the end of each stage, the IR list is cleaned up or replaced depending on the output of that stage. This process continues until we reach a max set of iterations, or if any of the stage does not apply any optimization to the IR stage, whichever comes first. For the MIPS stage, the optimizations applied are pretty simple. We apply an optimization to reduce the general register stack area for procedure definitions, which means that only the S and T temporary registers which are used in the procedure body are saved onto the stack, and only the T registers used in the procedure body are saved and restored at each function call in the procedure body. For the first part of the demonstration, I'm going to display the use of the compiler without any optimizations. So I have in front of me a sample input program which takes the input from the user and calculates the Fibonacci series for the given input, and then displays the element of the Fibonacci series at the given index. So we're gonna first build the compiler. And first things first, let's run the compiler at the end of the output stage and generate an output file. Since there were no errors, I should also see an output file created in the folder, which is by default called output.s. So let's run that through the SPIM simulator. So you can reinitialize and load the file and run the program, and it displays a string which is requesting a user input. So I enter the number 13, and it calculates the Fibonacci series and displays the element at index 13 in that series. Let's look through the compiler at its various stages. So if I change the input, command line input to the compiler and pass it the stage name, let's say scanner, it displays the output of the compiler at the scanner stage. So here are all the tokens which is generated as part of the input program. Let's take, for example, the symbol stage, and here we have the symbol tables which are generated as part of the program. As you can see, the first symbol table is the string table, which is a list of all the constant strings as part of the program. Then is the symbol table at file scope, which includes all your global variables and your function declarations along with their types. And then we have the symbol tables for each procedure scope and block scope. So before I begin demonstrating the optimizations which I've implemented in the compiler, I would like to discuss the test framework which I have available as part of the source code. So the tests are available in the project directory as part of the test folder. And if we run through the automated shell script, which basically builds the compiler and then passes the input programs which are saved in the test directory and compares them against. So the first optimization we're going to discuss is constant folding. I have in front of me a sample program which does a lot of arithmetic operations on constants, and the expectation is that these constant expressions are evaluated at compile time and replaced with the result of these operations to reduce the amount of instructions we have. So here is a comparison of the IR generated as part of the no optimization program as compared to the optimized IR output. As you can see out here, a bunch of IR instructions related to the first arithmetic expression which we have out here, which is simple addition of integers from 1 to 6, has been replaced by a single instruction which loads the value 21 into register T11, which is passed as an argument to the to the function call for printing the integer. And you can go by and look at all the other arithmetic instructions, and everywhere it sees only constants being evaluated as part of the arithmetic expressions. The IRs are basically replaced by the result of the operation. So for the next optimization stage, we're going to discuss algebraic simplification, which is all the arithmetic expressions which can be evaluated at compile time. For example, addition or subtraction of a variable with 0, multiplication, division by 1, we have left shifting by or right shifting by with 0, x odd with the integer value of 0, x odd with the value 0, and x variable ANDed with the value of -1. So we're going to look at the differentiation between the IR outputs generated. So for example, for the first expression, which is x plus 0, in unoptimized code, it evaluates to the 4 lines of code over here, which is then replaced by a single line of code which copies the value of T6, which is the loaded value of the variable x onto T7, which basically means x plus 0 is equal to x. You take another expression like division, which is division of the variable x by 1, which should also evaluate to the variable x, which then gets converted into a copy operation. We have another operation where we're multiplying a variable with 0, and that always evaluates to 0. So the mult operation is replaced by a single constant load immediate, and there are other optimizations which then go ahead and remove the redundant load word, the constant, and the address of operators successively, because they're no longer being used in the rest of the code. The next optimization stage we're going to discuss is conditional expression evaluation, which is anytime a condition expression can be evaluated at compile time, we can either remove or replace the code, the IR code generated for the if-else block. So here we have a sample program which has an if expression which always evaluates to true. So if we look at the IR code, we have 4 instructions here following the if expression, which is first the integer expression for 10 plus 9, which as discussed in the previous stage would lead to a single IR instruction loading the value 19 into the register T4. And since T4 now has a known value of 19, the go-to statement of if false always evaluates to true, so we completely eliminate the go-to statement. So that basically removes the complete block because of 2 successive optimizations which are done. This is also a good example to discuss dead code elimination. So since the go-to statement is removed by the condition expression simplification, the generated label 1 is now unreferenced to the following stages for dead code elimination removes the label 1 from the IR code list. And since that is removed, we now have a redundant go-to label statement which has a go-to to a label which is successively followed. So it basically can both be eliminated. So here we have a same program which is slightly modified so that the expression always evaluates to false, and the expression is since this is always evaluates to false, this piece of code can never be reached. So if we look at the IR code, again through successive rounds of elimination, we first start with the constant folding, which evaluates the value of the temporary register T5, and since that's always evaluated to be false, this is now replaced by a go-to statement. And any time we have a go-to statement followed by a bunch of successive instructions, those instructions are then removed until the label is reached. So these successive stages basically end up removing the entire block of code, which is represented here by the if statement. For the final demonstration, I'll be discussing the optimization stage as a whole, and we're going to be looking its effects on a sample input program which takes inputs from the user for a matrix, including the size and the elements of the matrix array, and calculates the determinant. So we're going to first look at the MIPS code which is generated and discuss the optimizations of the MIPS stage. So as I said, in the MIPS stage, the optimizations which are implemented are that the general stack register area is now optimized to only save the temporary registers which are used as part of the procedure body. So considering this procedure for absolute only uses registers from T0 to T7. So basically the following registers T8, T9 and S0 to S7 are removed from the stack frame, which leads to a huge save in the overall stack size, and also the saving and the restoring of the registers at the end of at the start and end of the procedure body. And so here's an example of a function syscall in MIPS, and as you can see there are no temporaries stored and restored as part of the stack. There are additional lines of code which appear different between the MIPS outputs, and they may be a result of the IR optimization. So we can look at the IR optimizations, and that also has a bunch of optimized code. So we can look at the multiplication operation, which is done by a power of 2. And the optimizer of reduction in strength has replaced the operation by a left shift with of the register with the value 5. There are other versions of optimizations which are kicking in. For example, arithmetic operation, which is doing multiplication of the values 0 and 4, which is then replaced by a constant value of 0. So this probably is an array access which is being done, and you can see a whole bunch of code which is different between the optimized and the unoptimized versions of the code. So there's a lot of savings being done in terms of both space and time. And we can quickly run through the optimized version of the code. So here I have the sample program. I reinitialize and I load the optimized version of the program, and it requests for an input. So I'm going to enter the matrix size as 2, and then enter the elements as 1, 2, 3 and 4, and it rightfully calculates the determinant as -2.